Hello everyone, my name is Haoyu. I'm a PhD student from the University of Kiel, along with my co-author Bob Stern, Yamrica Rojas Agramonte, and Antonio Garcia Casco. We will tell you about the temporal evolution of the Great Antilles convergent margin. The Greater Antilles Arc in the Northern Caribbean is one of the best preserved fossil interoceanic convergent margins on Earth. It is exposed in Cuba, Jamaica, Hispaniola, Puerto Rico, and the Virgin Islands. Spanning about 2,000 kilometers, igneous and metamorphic rocks of the Greater Antilles Arc record subduction of the North American plate beneath the Caribbean plate during Cretaceous and early Paleogene time. The Greater Antilles Arc collided with Bahama Platform and North America, stopping subduction in the west during Eocene, while slow oblique subduction continues in the east. In this project, we compile available geochronologic and geochemical data to understand what the Great Antilles Arc can tell us about how interoceanic arcs form and evolve. Here we only talk about the age complication. Sedimentary, metamorphic, and magmatic units develop in a subduction-related environment within the Great Antilles Arc. These are well recognized as passive margin of North America accreted to the overriding plate in Cuba, ophiolite and ophiolitic melange, Cretaceous and Paleogene magmatic arcs, and plume-associated igneous rocks. These four tectonic units are not developed on every island, but volcanic rocks are exposed on each of them. The Greater Antilles Arc formed over a south-dipping subduction zone. We identified four tectonic settings according to the location of rock units relative to the present position of the magmatic arc. These include Four-Arc Melange, Four-Arc Ophiolite, Cretaceous and Paleogene magmatic arcs, and the Richer Arc region, which includes both metamorphic and igneous rocks. Geochronologic and geochemical data published in the peer-reviewed literature for the Great Antilles Arc were compiled and assigned into one of these tectonic subdivisions. In Cuba, Four-Arc Ophiolite refer to the massif within the northern and eastern ophiolite belts. High-pressure metamorphic rocks within serpentinite melange intermingle with the ophiolitic massif are assigned to the Four-Arc melange. Magmatic arc units include island arc soleatic, calc-alkaline, and alkaline plutonic and volcanic arc igneous rocks. These include the Cretaceous arc south of the northern ophiolite belt and Paleogene igneous rocks of the Sierra Maestra. The Cangre, Pinos, Mabihina, and Escambray metamorphic terrains exposed south of the magmatic arc are assigned to the Richer arc. In Hispaniola, ophiolite associated with the accretionary complex are present in the Cordillera Septentrional and the Samana Peninsula. The Protoplata ophiolitic complex and the Gaspar Hernandez serpentinite peridotite within the Rio San Juan metamorphic complex are assigned to the Four-Arc ophiolite. High-pressure accretionary wedge materials within the Septentrional Cordillera are assigned to the Four-Arc melange. The Samana complex is not a melange, but because of its high-pressure metamorphic nature and the Four-Arc position, in addition to the occurrence of the akrajatic Ponta Blanca pentinate melange unit, it is assigned to the Four-Arc melange subdivision. Island arc soleatic and calc-alkaline series igneous rocks exposed in the central and eastern Cordillera, including volcanic rocks from Los Ranchos and the Maimon Formation and the granitoids, which are included in the magmatic unit. Igneous rock associated with arc rifting and backlash spreading in the central Hispaniola and unit associated with the Caribbean large igneous province, such as the Duarte complex and the Domicile Formation, are assigned to the Richer arc. Cretaceous and Paleogene volcanic and plutonic rocks of Jamaica, Puerto Rico, and the Virgin Islands are included in this study. Jamaican rocks are assigned to the Richer arc. Ophiolitic melange and peridotite belts of southwestern Puerto Rico are also assigned to the Richer arc. We compiled 597 published ages for the Great Antilles Arc. This study used different radiometric techniques. Half of them are potassium argon ages, while 25% use the argon-argon step heating techniques, and 20% use the uranilide zircon. About 6% come from rubidium strontium, Riemann-Osman, lutetium-Huffman techniques, and paleontologic data. In the age histograms for the Greater Antilles Arc, age runs from 30 to 155 million years ago, but the vast majority are the Cretaceous and the Paleogene. A systematic difference in mean age is seen between techniques. Uranilide zircon ages have an older mean of 94 plus minus 48 million years ago compared to the younger mean age from argon-argon and potassium-argon systems. This difference suggests that argon-argon and potassium-argon ages represent cooling or reset ages. which is particularly evident in tertiary potassium argon ages of Cretaceous volcanic arc igneous rock. In the age histograms distinguish igneous versus metamorphic rocks, Malunge-related metamorphic ages have an older mean of 88 plus minus 58 million years ago, and ophiolite-related metamorphic ages, or richer arc metamorphic ages. Igneous ages are similar to the two younger metamorphic ages. Some age peaks are seen, especially in the late Cretaceous, from 95 to 60 million years ago. This peak is shown in both igneous and metamorphic rocks, and especially clear in argon-argon and potassium-argon ages. Two subordinate peaks are observed at 120 to 110 million years ago and around 40 million years ago. The older peak is pronounced in Rhenolite zircon and Rhenian osmium ages, reflects both magmatic and metamorphic activity, including partial melting of the metamorphic rocks. The younger peak is dominated by potassium-argon and argon-argon ages, mostly reflects igneous activity. These differences are associated with the technique bias and potential resetting of the potassium-argon isotopic system. There is also geologic bias, the difference between Rhenolite zircon, which is mostly used for dating igneous crystallization, and argon-argon, which is often used for dating metamorphic events. The evolution of Great Antilles Arc can be useful compared to other fossil convergent margins, like southern Tibet, showing significant similarities and differences. They are similar in terms of spatial scale, both being about 2,000 kilometers long. Both systems began in early Cretaceous time, experienced prolonged subduction, and both were site of Eocene collision. However, ophiolites of southern Tibet are mostly the same age, whereas a wider range of ages found for Great Antilles Arc ophiolite. Metamorphic source of southern Tibet about the same age as around 120 million years ago subduction initiation ophiolites, whereas the Great Antilles Arc ophiolite sources are younger. Southern Tibet experienced abundant igneous activity when it collided with India, whereas the Great Antilles Arc does not show collision-related igneous activity. The wider range of ophiolite ages within the Great Antilles Arc might reflect continued fault extension after subduction initiation in the early Cretaceous. The formation of late Cretaceous metamorphic source and low titanium arc soleatic volcanism in the eastern Cuba is further evidence of a more complicated subduction history for the Great Antilles Arc. This might be due to the changing subduction regimes, the influence of the late Cretaceous Caribbean large igneous province, or both. The Caribbean large igneous province was active for at least 18 million years, from around 92 to around 74 million years ago, with the main magmatic activity from 89 to 90 million years ago, which coincides with the age peak observed for Greater Antilles Arc magmatism and metamorphism. Remnants of arcs with Caribbean large igneous province affinity in Hispaniola and Jamaica occur in the richer arc in our fourfold subdivision. The geochronologic data indicate a strong influence of the Caribbean large igneous province on the Great Antilles Arc. This suggests that strong heating of the convergent margin was responsible for significant melting and metamorphism. For instance, metamorphism of the Mabujina and Fulvolite complex in the central Cuba occurred around 90 to 93 million years ago, and this was shortly afterward intruded by plutonic rocks of Manicaragua basalts around 89 to 83 million years ago. Similarly, the Great Junco metamorphic soil and the onset of the abduction of the Moa Baracoa ophiolite may have been associated with the emplacement of the cliff plume head. Notably, Farrar de Pablo et al. 2020 have recently shown that plume-derived melt interact with supersubduction zone Loma Caribe peridotite of Hispaniola in a late Cretaceous background setting. These observations underscore the importance of further research into the age and nature of the Great Antilles Arc, and the possible influence of the cliff on this important and interesting convergent margin.